All right. Today we're going to be doing problem number 1 of homework number 6. What we're giving in this problem is basically a joint density function defined right here, whereby we have some unknown beta times xy defining the region between 0 and 1, where the x is between 0 and 1 and the y is between 0 and 1, but more importantly, that the x is less than or equal to y in this case, okay? And basically, any place outside this box, xy box, defined by 1, is going to be 0. All right? That's what we're given. This problem has 7 parts, so let's get started. Now, first and foremost, let's try to solve for this beta function and actually figure out what that has to be in order to define this as a true joint density function. Now, in order to do that, actually, might be jumping ahead a little bit. It's like I just drew this out right here, which I should outline. This right here, the xy term, is outlined by this line right here. Xy is equal on the xy plane. This thing is defined by this line right here, and because we specifically want values of y greater than or equal to x, it's basically everything in this box above this line, and also defined on 0 to 1 on the x-axis, 0 to 1 on the y-axis. So this is our region on the xy plane. Okay? Let's get back to it. Let's define what beta is, okay? Now, in order to, as we've done before, in order for this function to actually work, we have, basically, if we take the integral of the joint density function over the entire plane, we get the joint distribution, and that should equal 1. So we can use this formula here to figure out what beta is. Now, we basically plug in this right here, and then we use the actual limits on our integral to define the region right here. The way we do that is, like, first we define it according to the x-axis, okay? Now, as we can see right here, our x is going to be defined between 0 and y. So that's why we have these coordinates right here. And once we define our x, okay, we define our coordinates on y, which basically y is going to be between 0 and 1. So that's how we define that right there. And then we do our double integration formula right here. We bring out the constant within the actual integral right here, the by. We integrate according to x. The x left in there, as we can see. This breaks down accordingly, okay? This whole thing's going to be x squared over 2, from the upper limit of y to the lower limit of 0. Lower limit of 0 is 0, so it's going to end up being y squared over 2. So we have this formula here for the outer integral, all right? Which actually breaks down, you can bring this right here, it's going to be y cubed with a constant of beta over 2, which we bring out right here. All right, so this is our equation. All right, you can see how the integral from here, the integral formula for this is going to be y to the 4th over 4, which we figured out from 0 to 1. We can see how that actually equates to being 1/4 right there. So beta over 2 times 1 over 4 is beta over 8, which, as we said here, is equal to 1. So we can see how this beta has to be the value 8. So our final answer right here is, if substituting our value for beta, our joint density formula right here is going to be defined as 8xy within this box region on the xy plane, and 0 otherwise. Now, part 2. Part 2 asks us to figure out the marginal density functions defined based on our joint density function, okay? And not only that, but to sketch them. All right, how do we do that? Well, we take this formula right here, and in order to find the marginal density function according to x, we integrate over the joint density function in regard to over y. Okay. Similarly, to find the actual marginal density function according to y, we have to integrate the joint density function according to x. That's what we do here. All right. So, as we know, if we're integrating over y right here, all right, we substitute this in here over dy. How do we actually figure out these coordinates according to y? Well, we look right up there again. All right. Basically, our y is going to be defined lower limit of x, upper limit of 1. That's what we get right there. We integrate according to y. The 8x is a constant we bring out. This ends up being y squared over 2, evaluated from 1 to x. We do our arithmetic. We take off constants right here. And our final answer is going to be 4x times the difference of 1 minus x squared. And that's specifically defined on the x-axis from 0 to 1, which makes sense, and it's 0 otherwise. Similarly, if we want to figure out the marginal density function according to y, we do a similar maneuver right here. Notice how these are the same. The only difference is actually our limits have changed, which makes sense, okay? Because if we're doing limits here according to x, all right, we can see it's going to be between 0 and 1. And that's what we have here. We do the same arithmetic. We just solve it on these limits right here. And what we get is 4y to the third between 0 and 1 on the y-axis and 0 and 1. And if we draw those out, we can see how this equation right here, all right, on the fx plane, how that actually works, it breaks down, all right, because basically what we have here is a function drawn like that, only defined on the between 0 and 1, ends up being this curve here. And for 4y to the third right here, we're going to actually have define this cubic function from 0 to 1. Y over that. So those are our sketches. Now, for C, basically we have to prove whether x and y are independent. All right? We're told that basically if x and y were independent, then the actual joint density function should equal the actual product of the two margins. All right? So if we actually take these two formulas right here, multiply them out, if it were independent, we would hope we would get this formula here. So we do that. And what we get is this formula, 16xy cubed times 1 minus x to the third, which obviously is not equal to 8xy. Hence, x and y are not independent. Now, part D asks us to actually figure out the expected value according to x, expected value according to y, and the expected value according to xy. All right? So how do we actually find the mean? Well, we do it like we did before. I mean, x and y we've done in previous homeworks. All right? Basically, we take the marginal density function and multiply it times x and find the integration from negative infinity to a positive infinity. We do a similar thing for y, which we do right here. We use the marginal density function according to y. We do our arithmetic right here. Okay, we factored in the x right here. We're going to figure it out from 0 to 1 because that's our entire region on the x-plane. All right, we do our arithmetic right here. We basically multiply out, take out a 4. We can see how this breaks down into how the integral breaks down into x to the third over 3 minus x to the fifth over 5 from 0 to 1. 1/3 minus 1/5, all times 4. And we get 8 over 15 for the expected value on the x. Similarly, if we do it right here, again, we're doing from 0 to 1 using our marginal density according to y. See how this is going to work out to be a y to the fifth over 5 from 1 to 0 again. This is equal to 4/5. Now, we do it according our expected value by the joint, the xy. We have to do the double integration, and we have to actually multiply times our joint density function by xy. All right. So as we use our original joint density function, when we multiply by xy, that's why we get x squared and y squared in there. And again, we integrate according to the functions. I mean, we did this already, okay, from 0 to y, and then 0 to 1. We do our arithmetic, as you can see here. Let's work it out. And our final answer ends up being 4/9. Now, part E asks us to figure out whether x and y are uncorrelated. Now, if it is uncorrelated, excuse me, a little uncorrelated, then basically our function, this should be true. Okay? So if we take our values up here, 8/15 times 4/5, that ends up being 32/75, which is not equal to 4/9. Hence, this is not true. Hence, it is not uncorrelated. That's our E. Now, for problem F, we have to find the conditional probabilities. Okay? The conditional values. The conditional density functions. First, x given y, and then y given x. And then we're asked to sketch these. Okay? And what we do is basically use the formula. When we use the conditional density functions, basically we use the joint density function over the marginal density function of the given. So in x given y, we're basically use the joint density function over fy. In y given x, we're using the joint density function over fx. So basically we use the formulas that we calculated earlier. We cancel out, and our our conditional density function x given y ends up being 2x over y squared within the region where x is between 0 and y, otherwise 0. And for fy given x, we get 2y over 1 minus x for the region between x and 1. Okay? And that's our form. That's f. And if we sketch that out, we get these functions right here. This is x according to y, which if we can see right here, we mapped it out according to the region from 0 to y on the x-axis. So assuming, y can be any value from 0 to 1. It draws out from 0 to the y value. Y could be here, here, and even could be 0 to 1. This is how it works out. Similarly, for f, y given x, we have the function down here, but notice how the line is only defined on the y-axis from x to 1 for similar reasons. All right. And I listed that out right there. Basically, you can see why we drew it. Y is a straight line. We can see how if it's a function with independent variable of x, for the conditional one, x given y, we have a constant 2 over y squared. All right. Over here, we have a constant 2 over 1 minus x squared. So that's another one straight line. Finally, we do G. G asks us to find the conditional values, the expected or mean values of y given x, y given a specific x, and then the expected values of x given y, or the expected value of x given a specific y. All right? So we note right here that these two functions are going to be very similar, and these two are going to be similar. If we get this, we're going to basically substitute a specific x for this, because this is a generic x. Similar here, if we get this, we have this value. All we do is substitute in a specific y for a generic y. So when we calculate things out, how do we figure this out right here? We use our conditional probability function. When we multiply it similarly to the other expected value equations, we multiply times y. So we work out the arithmetic, again from x to 1. All right. And this is the formula we get. We get 2/3 times 1 minus x squared over 1 minus x cubed over 1 minus x squared. That's our equation right here. And we get this accordingly. All we do is substitute a big X. It's the same equation. Similarly, if we do the expected value of x given a generic y, use a similar form. We just multiply times x. Work out our equation. What we get is 2/3 times y.
So our expected value of x given a generic y is 2/3 times y, and if we have a specific y, it's the same thing, just big Y. And so ends our problem number 1.